Welcome to the talk. When we submitted something a while ago, we submitted literally something, the Android something, which I thought was amusing and also true. We didn't actually know until last Friday what we were going to do. 2 weeks ago, we had a really good idea, and then we got about a week in, and we realized we're never going to finish that in time, so we switched. That's why I like submitting titles like this. So it turns out that our talk today will be on graphics and performance. I hope that suits everybody. Otherwise, there's lots of other talks going on right now. Frame metrics is an API that we introduced in N that you can use to get way more detailed information at the app level. Turns out that this is a capability that we already had on the platform. You have seen it in action. Well, at least I hope you have. If you run ADB shell dump sys gfx info, you get a bunch of numbers on the screen. We'll show some of that later. We now take that same information and can push it into your app. So instead of actually needing to be connected to the device and run it, at build time or at development time to see what's going on, you can get this information in your app at runtime and aggregate and do whatever you want with it. So when you're using the device and you want to do profile GPU rendering, you can click on that helpful radio button on screen as bars, and then you get this nice little colored thing there. And if I had done my homework completely, I would have replaced this slide with a more helpful screenshot, which would describe what all of these colors are. We'll get to this later because you can actually see in the data what's going on there. But basically, these are the different portions that go into the rendering and UI interaction in any given frame. You have processing of input, processing of animation, actually constructing the draw commands, and then pushing them to the GPU, all of which make up the frame. And then you want to try to stay below the magical green bar that represents 16 milliseconds or 60 frames per second. So we've had that one for many, many releases. I think you did that in probably Honeycomb or ICS?
ICS, I believe.
And then it improved over time. I think it originally was just text output that you could get at the command line, and then Romain wrote the thing probably in ICS to pop it up as an overlay, which is really weird when it happens when you're not expecting it. It's in like every window on the screen, and then you realize there's many windows in parallel all the time.
QA found a lot of bugs about this one. They thought it was an artifact of the rendering system.
Well, it sort of is. So hopefully you've used that and you've seen it, and you've seen better screenshots than that one. Here's what happens when you run it at the command line. When you say dump sys gfx info, you can run it overall, and it'll tell you the same information for all of the active processes, or if you run it on a particular activity, then it'll tell you the information there. So I can step through this really quickly. Romain can probably give you even more detail. It's aggregating all of the data. It's on a per frame level, it gets all the timing information for each one of those things that I talked about: input, animation, draw, execution, and it aggregates those into a histogram. So you can see this looks kind of nasty, but you can you don't have to extrapolate too much to say, well, I could just take this data and I could dump it in somewhere and look at it in an easier way. But this basically tells you how many samples are in each one of these buckets that are aggregated over whatever period of time it was collecting data over. It also gives you helpful information like not just what was your average frame time, that's nice, but how many frames were way higher than you expected. And how many frames, essentially if you're janking, 1 out of 1,000 frames, either it's erroneous data because, well, you happen to be, during a transition between activities or whatever, or it's a glitch in the data, or, something got dropped there, or, okay, you were too high once. That's fine. But if you're actually missing a lot of frames, if you have a high jank rate, that is something that you should be concerned about.
Yeah, and the key takeaway here is that we hear about frames per second a lot when it comes to performance of applications or games. Frames per second are actually not that good of an information because they are by definition averaged over a certain long period of time, at least a second. And you could have dropped a few frames but still get a good frame rate. So we don't like to use frames per second, especially on Android where we render only as needed. So you could be getting 10 frames per second, but it might just be because you have an animation on screen that's only requiring 10 frames per second, which is why we use this information instead. So when you look at this as this dump, and if you want to create dashboards from it, I really suggest that you look at the percentile numbers here. So we can see in this example that the application, whatever Chet measured here, system UI, oh, we should tell someone about it. That's bad. The numbers are bad. More than 50% of the frames were above 19 milliseconds, which is more than the 60 millisecond threshold if you want 60 frames per second. So yeah, look at the percentile, and you really want your 90th percentiles and higher to have good numbers there. Those numbers are really, really bad.
So as I said, a lot of these capabilities have been in the platform at least since ICS, but there have been improvements over time. The aggregation of the data into something probably more useful, into these buckets, this histogram, I think dates from N. The other interesting thing is we're always collecting this data at a native level, very low level, like we're always recording that timing information. I believe when Romain first implemented it, we were only turning it on if you pulled up the dialog in the device and you said, I would like some graphics info, and then you would do something for a couple of seconds, and then you would spit out the data. But we're doing it continuously on your behalf, which means that at any time you can query the system and see what's going on, and we'll have the data for that period of time preceding it.
And we're expanding this kind of capabilities. In O, we're adding an OpenGL extension that will let you query timing information outside of your application. So those values are everything that your app is doing, but then there's the work that the GPU and surface fingers must do after your app is done. And we cannot query them for everything yet, especially if you have a custom surface view or you custom GL drawing, or if you're a game or camera app. So now, thanks to that OpenGL extension, you'll be able to query Surface Flinger for more information that you can use to make pretty dashboards.
So this is the new presentation of the data. The old and still existing presentation of the data is the sort of per frame duration. So when Romain first did this, I think this data would comprise of like 3 or 4 different metrics. It was total duration of the frame, and then the larger chunks of actually creating the drawing commands and then issuing the drawing commands to the GPU. That was probably the core 3 that we started with. Now there are a lot more. There's a lot of really confusing numbers there. Don't even try to parse this by eye. That would be stupid. Instead, you can imagine these are comma-separated values. Put it into a spreadsheet. There's going to be some header information about what the timing values are that we're actually spitting out here, and then you can start to analyze your data. Right, so you get this on the command line. You can basically say dump sys GFX info of a particular package. Frame stats. You give it the frame stats command, and it's going to give you all of these durations for the frames. And it's going to give you a whole lot. I put some helpful ellipses down at the bottom.
Aren't those timestamps? They're not durations.
They
look like timestamps.
OK. They are timestamps. Those are really big number. Boy, our durations suck. Yes, timestamps. All right. So that's what we're doing. That's what we're tracking at the native level, and then we aggregate it into the helpful histograms. But there was no way for you to get this outside of ADB or outside of looking at the colored bars on the devices until N. Now we have an API. You need to add a callback to a window, and your callback's going to be called back on every frame. And then you're going to listen for these frame time events and do whatever you want with them. We're going to tell you these timestamps, or actually duration values, and then you can collect them over time, aggregate them, put them into histogram buckets, tease out the ones that you want, analyze them however you want. You can upload them to your own data cache somewhere, analyze them offline across your user base or some select user base. So the basic API works like this. You get the window, you add a listener to it, along with a handler. Your listener looks essentially like this, on-frame metrics available. You will be called on every frame. Frame metrics is the key data structure that you care about. Drop count doesn't refer to drop frames, but rather drop data elements. This happens really, really frequently. So if you waste any time in this call, we're going to drop some frames because we would rather drop the data than wait for you to come back and completely screw up the data. So we're going to tell you anytime we call you, here's how many frames that we had to drop in order to get you the new data. And then inside of there, do whatever you want. The suggestion is that you quickly copy that data and then chuck it off thread to be analyzed, aggregated, composed, whatever you want to do with it, so that you can quickly return because it's waiting for you to return and is dropping data on the floor while you are not returning. The data that you can tease out there is whatever you want out of that selection that we went over before, input animation, total duration, obviously total duration, some of you are going to care about, but if you care about some of the other sub-elements in each frame, then you can grab those as well. All right, I love this math. If you render at 20 milliseconds a frame, you can still get 60 frames a second. We actually changed the way the math worked in N? Was this MR1 or this is core
It was
N?
in MR1, I believe.
MR1. So neat little performance hack. I was going to quickly walk through and try to explain this. It's a bit tricky. So here's a complicated graph. We will step through incrementally. You can imagine these vertical sync pulses coming through every 16 or so milliseconds. So each one of those is going to hit. And I'm going to show you the two models that we've worked in traditionally over the last several releases. That's the one we referred to with previously, and then Hardware Composer 2. So we would have touch events processed on a vertical sync. We would also have UI happen on the vertical sync, so basically everything sort of starts in concert. We start doing this work. We also process swaps. So Surface Flinger on a vertical sync would say, okay, now we need to actually display this thing on the screen. So we have the swap happening on every one of those frames, which means that's the window where the user can actually see the effect of stuff that we had to deal with in order to create the new visuals on the screen. So we have touch that happened way over there on the first vertical sync on the left, and then the user is going to see the result at one of two times, either 32 milliseconds later or 48 milliseconds later. And the reason is they touch the screen, the touch events get aggregated, sent up to the Java layer, and then we process those events. We make any changes in the UI that we need to. We do layout, we do rendering, we toss stuff onto the render thread, et cetera, et cetera. Eventually, if we're double buffered, we will flip the buffer on, do I have a mouse? Yeah. So we'll flip to the back buffer at this point, and then Surface Flinger is going to display the results here. So in the best case scenario, we render within 16 milliseconds, and the user sees the result 32 milliseconds after the touch events got aggregated, right? In a typical scenario, in a typical application, occasionally you're going to drop a frame, and when you do, we will go into triple buffering mode, which increases the latency for touch events, but it makes things smoother because we're no longer like waiting for buffers to be free if they're going to take a long time to render, but it means there's an extra 16 milliseconds built into any interaction scenario, which means they're going to touch the screen here, or the touch events are going to be aggregated there, and then 48 milliseconds later, they're going to see the results. So we go into Hardware Composer 2, and now we've shifted things a little bit. So touch and UI stuff now starts getting processed 4 milliseconds in. This is kind of a mystery to me to understand, but essentially what we're trying to do is reduce the latency between when the events are actually getting processed. So we're given a little bit more time on the front end for touch events to actually be aggregated before we start doing anything with them. So we give that an extra 4 milliseconds. And then 4 milliseconds after that, we can do a buffer flip with Surface Flinger, but it's still doing the swap on the vsync, because that's actually when the pixels get displayed. And now, what we have is the user seeing the result at still the same frame over here, and that is a more typical scenario. So what's actually going on with the magical 20 milliseconds is now we have 4 extra milliseconds for them to touch the screen and then for us to react to it. And then we have an extra 4 milliseconds built in before we have to get the buffer from Surface Flinger, right? So now we have the 16 milliseconds in between these events, plus the extra 4 millisecond delta between the touch event and the syncs on which we're actually doing the buffer flip. So you effectively have 20 milliseconds to process that information. And then the user is going to then see that result there and probably not get triple buffered, because instead of your application having to stick within 16 milliseconds, we now gave you an extra 4 milliseconds of slop. So it's more and more likely for the application to have enough time to stick within the frame boundary and for us to not flip into a triple buffering mode. So now instead of seeing the result 32 to 48 milliseconds later, the user is going to see the result of touch input interaction 28 milliseconds later. So yay.
All right, Async Layout Inflator. That's a new class that was introduced in support library v24. It's in the v4.view package. And the name pretty much says it all. It inflates view in an asynchronous manner. It spawns a new thread that has, usually it's called thread number 2 when you look at profilers, so it's a little difficult to find. But that's where it tries to inflate views. So this is what the code looks like. It's fairly simple. You create your layout inflator. You have to give it a context. Here I'm just passing the activity, which is probably a bad idea because it's going to keep the reference to that context for quite a while. And then you call the inflate method. So it looks very similar to the layout inflator, the regular layout inflator, The big difference, so you still pass the resource ID, you still pass a parent, but you don't have that Boolean at the end. And we'll see that's one of the limitations of the new Async layout inflator. What you pass instead is a callback, and here I use the lambda notations, which really confuse Chet. So the listener, the callback, gives you back the view that was inflated, the resource ID that was inflated, and the parent that you wanted to inflate into. The async layout inflator will never add the inflated view for you into the parent. You have to do it yourself. So here what I did in this example is I'm actually playing an animation in the UI, and while the animation is running, I'm inflating the view. So I just have a bit of logic to say, if we're already done with the animation, then I can add the view, and if the animation is still running, I want to keep the reference to the inflated view to add it to the UI once the animation is done running. So it's a very easy way for you in your application. If you know that you're going to have idle periods for the user in the app, that you can use that time to prepare the views you're going to show. For instance, if you have a view pager, you might want to inflate the pages on the sides ahead of time in the background. Now, this is really useful, but there are a lot of limitations to this API. The first one is that the inflator must be created on the UI thread. So far, that's very similar to a lot of the APIs that you have in the framework. Inflate views cannot create their own handler. They also cannot call looper.mylooper. That will crash. So if you try, for instance, to inflate a web view using async layout inflator, it's very tempting because web views are usually very expensive to create. You're just going to crash. When it comes to thread safety, the UI Toolkit never made any promise. We never wrote the code with this kind of use case in mind. So who knows what's going to happen? It might work. It might not work. We don't know. And the behaviors will probably change in the future if you change the number of cores in the device, race condition, threads, all that fun stuff.
We encourage application developers to test their applications.
You can see that as embarking on an interesting journey. It's an adventure with us. Like I mentioned, the new layout inflator does not add the view automatically to the parent. You have to do that yourself for obvious reasons. You cannot use layout inflator.factory. I think very few applications probably rely on that. Fragments are not supported. I'm sure Jack is really bummed right now. And another fun tidbit is, it tries to be helpful. So if for some reason you're inflating a view that is not thread safe and it happens to throw an exception, you're actually lucky because most of the time, threading issues do not lead to exceptions. But if it does happen to throw an exception, it will try again. It will try the inflation again, but on the UI thread this time. And maybe this time it's going to work. Most of the time it probably won't if it's a real exception, so it's just doing the work twice and just delaying the time when you're going to get the exception in your logs.
So given this many caveats, it's a wonder that we're talking about this at all. I think the real thing to be aware of is if you have a custom view, that's when these kick in. If you're using one of the standard, especially simple views, we've tried it with that. Like the thread safety is not an issue. We're doing things in the right order. And okay, it's still worth testing.
Have you tried all the attributes and all the code? Yeah.
All right, still worth testing. But for the most part, it should work with standard views. But in custom views, we have no idea what you're doing in your code. So then you'll have to see whether the caveats apply.
Which leads us to systrace. We've talked about this tool many times in the past, and just out of curiosity, how many of you have ever used systrace? Okay, so that's the typical answer. I have a quote from Tim Murray, who's our profiling/performance expert on Android, and this is what he has to say. According to him, there is no other profiling tool that exists on Android, and he's kind of right.
I've heard that there are some new profiling tools to check out. But this is a really good one.
So systrace is very easy to use. It's part of the SDK. It's in the platform-tools directory. To invoke systrace, you have to make sure that ADB is in your path, in your shell. It's just a Python script, so you call systrace/systrace.py, and then you have to specify the tags, the different categories of events that you want to log. If you don't pass any event, depending on the version of Android, we're going to log like a different default, different set by default. What I like to use is those tags. So frec shows you the frequency of each CPU. It's extremely useful because what I don't like about some of the performance tools out there, for instance, they will show you the CPU usage. They will say, oh, you're using 100% of the CPU, and it leads you to believe that you're doing something wrong and your application is using too much CPU. But if the CPU is running at 200 megahertz, it's fine. Your application is doing really good. Now, if you're using 100% of the CPU at 2 gigahertz, that's a different problem. But that's why you want to see the frequency of the CPU. And also, once you start looking at systraces, you'll notice very often you might notice janks in your application that could be tied to the CPU frequency changing. So we try to, those are problems that we need to fix on our side usually, and we're constantly changing the scheduler and the way we boost the frequencies and the way we go back to idle frequencies. But it's a very important piece of information to have before you make any decision about optimizing your code. Sched is for scheduler, so that's very interesting. It's gonna show you what processes and what threads are running on what CPUs. And that can be very useful to debug different profiling issues, very often tied to processes or threads waiting on one another. GFX will show you what happens with the drawing subsystem. View will show you everything that's related to views, so measurement, layouts, inflation. Res is everything related to resources. So if you load drawables, stuff like that, they're going to show up in the traces. And WM, so window manager, will show you extra information, especially in Surface Flinger, to give you a better idea of what frames are scheduled when and how much time they take end to end to go to the hardware.
Just to be clear, like the things that you're specifying there are basically the different modules in which we have added traces. Yep. So the reason you're getting any information at all is that we've gone through and manually added tracing code to different things during the processing of Android code. So we have tracing for animations and for view processing and the stuff that he listed here. There are many more modules that you could choose to include, but basically this turns those on and says, okay, now spit out the information from tracing in the following modules of code.
And there's another module called app that's for applications. So if you use android.os.trace, it's a class that only has, I think, 2 static methods that you can use to add tracing to your application. You have to add the app category to see those traces appear. The nice thing about traces is that they're really lightweight, so they won't impact the timings of the measurements. Don't call it 1,000 times per frame, like at some point it does add up, but most of the time it won't be noticeable. So the output of systrace is an HTML file, which is nice because you can just open it in Chrome and you can just attach it to bug reports or whatever. So this one is a trace that I took in the emulator last night with the Async layout inflator, which is why I have an Android device with 12 CPUs. It happens to be my Mac Pro. Apparently, when you emulate a Nexus 5X on the Mac Pro, you get 12 CPUs, which is not quite what the Nexus 5 has. Anyway, so this is what systrace looks like. So here we have all the CPUs and what they were doing. So the best way to navigate systrace is to use the WASD keys. So if you've ever played Doom or any first-person shooter on a computer, you'll be familiar with that. So you can zoom in and out and scroll. So if we zoom in on one of the CPUs, and you have to zoom in pretty far, you can see the name of every thread that was scheduled, when it was running, for how long, what process it belongs to. And you can see effectively what every CPU is doing, and you can see a lot of bubbles here, which means we did not have enough threads to feed the CPUs. And that's important when you look at other events. So then for every process, you're going to see a bunch of different categories. Some of them are threads, some of them are counters. So the one that we're interested in here is my application. So that was just the demo app I wrote for the Async layout inflator. All those counters here come from the GFX tag, so HW UI, that's the name of our OpenGL renderer. If you click on them, you're going to see values here. They're used for internal usage. So for instance, texture count just tells us how many textures are in memory at any time. So right now we have 99 textures. And as your app is running, you'll see that number go up and down. That can be useful if you're doing a lot of bitmap manipulations. The parts that are more interesting, you can ignore the HWUI tasks. So here we have the render thread. That's where all the rendering happen. Every little F is the signals a frame. That's when an actual frame started. So you can zoom in on it if you want. You can see how much time the actual drawing of your app took. And when we look at an event on the CPU, every block here has a name. That's the name that you specify in the trace. So if you use that API android.os.trace, you can put any name you want. But just above, there's that little thin line, you see green here. And those are very interesting because green means the thread was actually running. It was scheduled on the CPU. White means that the thread was sleeping. And there's also uninterruptible sleep, and blue, which means that we're waiting on something. So those can be very useful because, for instance, here we can see that we took, 15 milliseconds to go through the frame, but we spent the bulk of our time sleeping. We were probably waiting on the hardware or another process to do some allocation. And we could investigate by matching, if you press the M key, for instance, you can easily see like what the rest of the system was doing, and you can get an idea of what was happening. If you want to know the shortcuts, just press question mark, and there's a ton of useful shortcuts you can use.
Did you want to talk about the tips in the frame bubbles?
Yes.
I don't know if there's like a yellow or a red one.
There is a red one. Yeah, that's a good point. When you click on, for instance, here there's a red bubble for a frame. If you click on it, you get a detailed explanation of what was happening and why that's bad. And you're going to see some of those explanations in a lot of places. Like when you click, what's on the UI thread. Here, for instance, when you click on choreographer.doFrame, it tells you what it's doing. There's a link to the documentation, so you can learn what all those things are in the system. Anyway, so what's interesting, if you look at the UI thread, we can see that the app was starting, and the app was doing a lot of random stuff, like it was trying to schedule the first frame. It was probably doing a startup animation, layout, all that kind of stuff. And here, there's this thread called thread2, and if we click on it, we can see there's an inflate tag. So that's the async layout inflator doing its work in parallel with the UI thread while we are trying to render an animation. And it shows you that because the UI thread was green, the UI thread was busy doing things. So we successfully parallelized about 19 milliseconds worth of work on the worker thread without blocking the UI thread, which is excellent in our case. And you can get an idea of why the UI thread was busy, because here you can see those other tags called animator colon. Those are special tags that can cross multiple events. They're automatically generated by the animation system. And they tell you that we were animating the scale, the translation, and the elevation of one or more views. And you can see for how long. So if we click on one of them, so we had for 15 seconds, yeah, we were animating a scale. That was the code I added to make sure that we could see all those traces. And that's pretty much all there is to systrace. A lot of it, learning it takes some effort. I really encourage you to try it and zoom in and try to correlate like different events across processes and to see what was scheduled on the CPU. And you should be able to find a lot of very interesting information about your application. And also because it is so lightweight, it's not going to affect the timings too much compared to TraceView, for instance, when it's not in sampling mode. And the numbers are a lot more trustworthy.
One of the things that's worth doing is if you're seeing a lot, if you're using frame metrics, and you're seeing a lot of janks or missed frames, then you can use systrace to find out when those are happening and drill down into hopefully what is actually causing them. There's information in there about when the vertical syncs happen, so you can correlate those with the operations on the UI and the render thread and see those frames where the render thread was taking a little bit too long and pushing into the next frame, and then you can try to figure out, was I doing layout during an animation? Am I doing too much work at the wrong time?
It's not just for UI. If you do anything with multiple threads, you're going to see all your threads here, so you can make sure that you're scheduling all your worker threads for your backend correctly. You can enable the I/O tags, the network tags to see how you're talking to your servers. So it's a very, very useful tool. Take a look at it.
So I think one of the things that's obvious in the field of software engineering to anybody that's been working in it for a while is that all the new stuff that we're doing all of the time isn't new at all, and we just keep redoing the same things over and over and over again in new languages and platforms and frameworks and libraries, and it's fantastic. It's job security forever.
It's the best chem in the universe.
So an example of that is in Android 1, Romain wrote what, a blog article or?
Yeah, no, so everything that Chet's going to talk about was actually the first public demo I published for Android. So for Android 1, we had some time left after we shipped the Android to the carrier. So I wrote this little application that would manage a library of books. So the books, you could see like beautiful book covers that were stored on the SD card, and back then those devices were really slow. So I spent a lot of time writing an adapter for ListView that was trying to be smart, and it was guessing the scroll directions. It was looking at how much time your finger was on screen every time you interacted with the list, whether it was during a scroll or not, to try to guess what list items should be prefetched. So it was trying to load like all those book covers ahead of time as you were scrolling really quickly. It was also scheduling, canceling, doing all that stuff. It was not easy to write, and I think very few apps have been doing that since then. And in RecyclerView now, we have a system that's a lot easier to use because you don't have to do it all by yourself.
So fast forward about 10 years, and one of the people on the UI Toolkit team, Chris Craik, did some work to look at what was actually happening in systrace to make RecyclerView so darn expensive. Like RecyclerView, just like ListView, is one of those core components that so many apps depend on. And a common thing that users are going to do is scroll or fling that list, and you get these janky frames as new content comes onto the screen. So he took a look at a lower level about what was happening when and what we could do about it. First of all, let's talk about how rendering actually happens during each frame. These are sort of the big blocks of functionality. So first, we have that input. This relates to stuff we've said before because, again, there is no new information in software. So we process input first. We figure out what we need to do about that. We process animation. We're going to change some properties. That's going to cause us to potentially invalidate and redraw stuff. We handle layout if anything needs to be actually measured and laid out. We actually draw this stuff. We create OpenGL commands or lower-level display list commands out of the stuff that we need to actually render onto the screen as a result of all the other processing that we just did. And then we sync up with the render thread, and then the render thread down below takes care of actually displaying the stuff into the buffer by calling OpenGL. So that's what happens on every frame ad infinitum. So this is a different and more complicated way of looking at this. This is several frames. Pretend that there's a recycler view that is well-behaving. There's no new content coming on the screen. You're just doing a scroll or a fling, and it's doing the same work on every single frame, and it's doing it very well and very quickly, and it's doing it inside, the important part, inside the frame boundaries, right? So we have input, we have animation, we're doing layout, maybe a little bit of work there, and we're recording the drawing commands, we sync up, the render thread does its thing, and it's all happening inside the 16 millisecond boundary, so life is good. Time goes on, and then we hit a situation where all of a sudden we have to do more work on input. The user is moving that recycler view, and it crosses one of those item boundaries, and then we need to reach out and actually create and bind a view. Right? And that means that input could take longer, which is going to push out all of the other phases. It's going to make it the time period where we sync to the render thread is going to be pushed later in the frame. And the render thread could easily be pushed so far over that it's going to take longer than that frame boundary to finish its work, which means that we've just missed a frame and the user's going to see jank on the screen. So what is going on inside of inputs in general? Yeah, that is basically what I just explained. In general, we're doing creation of views and we're doing binding of views, and these tend to be very expensive, depends on what you're doing. And we would encourage developers to be as optimal as possible because this really is the bottleneck for that exact action there. The faster that is, the less all of this is the general problem, but we understand there are complicated situations. Sometimes that takes longer than it should, and that's what causes the problem here. So wouldn't it be nice if we didn't have to stop in the middle of this input action to go ahead and do all this other stuff so that we could not push everything out the way that we just did? Wouldn't it be nice if we could do that before? And that's the premise of what Chris did. So based on the scroll direction, the information and these heuristics that we know about this recycler view, like, well, we're moving down in the Y direction, and we know that there's an upcoming item there, why don't we go ahead and eagerly do what we need to the frame before so that that information is just ready to go. So we do that, and we do the create, and we do the bind in a free space in the previous frame. Now, one of the interesting things about render thread is, I mean, in general, you might think, well, you're just doing the same thing. It's just that you're using more cores to do it, right? We have to do all the same information, then we hand it over, then somebody else does their work there. It's not like we can parallelize render thread with the UI thread because the render thread information in general is dependent upon the information that we generated on the UI thread.
We could.
He has some ideas about that, but this particular render thread action needs the information generated in the draw step in that frame. Right? We can't actually do that render thread in parallel, no matter what he says. But what we could do is we could use the downtime in the UI thread to do something else. And in this case, what we're doing is we're using the information that we know about the recycler view to say, well, we think we're going to need this information, so why don't we go ahead and generate it here, and then later in the next frame, we've already done that work and generated the information that we need so that all the drawing phases are shorter, and we can then fit that future render thread's rendering action into the frame boundary again, and life is good. There are a couple of caveats. What if the new item is not needed? So what if we said, yeah, we're going to need that new item really soon now, and we go through all that effort, and it turns out the user stopped at that exact moment, or something else happened such that we didn't actually need it on the next thread, so we wasted that effort. Okay, so we wasted a little bit of effort. But in general, that's not the case, right? If we're actually moving, most of the time we're going to keep moving and actually need that next information. We are talking about frame boundaries. We're not saying a second and a half from now, 70 frames later, we're going to need that. We're like, no, 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 we're just about to need it. So in most of the cases, we actually are going to need that information. There are also situations where there is no render thread. Render thread came along in Lollipop, and therefore, if you're running on a KitKat device, then you're not going to have a render thread. So that stuff that we're doing earlier isn't really going to buy you anything because everything happens serially anyway. But it's work, we're moving when that work happens, but it's work that has to happen anyway. So it's not going to give you an advantage on earlier releases, but you're not going to suffer because of it. There's an article that we posted on medium.com if you want all the details in a few more words than I've used here. It's available in support library v25, so it came out, I think, in late summer, and then there were more enhancements that were made in 25.1 in the fall. We built it into all the default layout managers for RecyclerView, so if you just use the defaults, then you get it for free. If you have a custom layout manager, then you should override collect adjacent prefetch, not prefect positions. This code will not compile on this slide. Then you need to override this to do something intelligent. In the default layout manager, it is stubbed out. We do enable prefetch by default, and you can toggle that. You can set that Boolean value as you want, but you will want to override this.
All right, now I want to talk about bending. So I'm sure you've all seen that problem on your phones at various times over the years. So I tried to recreate the effect on the slide. I'm not sure it's visible, but you should be seeing like, well, bands in the background. I did that in Photoshop. And I want to talk about why this happens, and if it does happen, like, first of all, what Android is doing to fight bending, and what can you do about it? So where does it come from? The problem is it's a quantization of a signal. So I'm going to show you a practical example. Let's say that you have a vertical gradient that goes from white to black, and you put that gradient as the background of your application. So it's going to cover the whole screen. Let's say you're on a Pixel XL. The screen is about 1,440 pixels high. So what's happening is that we have 11 bits of data for the positions to cover the 1,440 pixels, but we only have colors that can use 8 bits. So we're trying to spread 8 bits of data over 11 bits of data. So we're losing information.
Actually, I have a question about that. At least on earlier devices, we have theoretically 8 bits of data per color channel, but the displays themselves would actually have
Yeah,
less,
the
right?
displays themselves had less. Like the very early Android devices, they used to have like maybe 5 or 6 bits per channel.
So it was even worse, but maybe that's not a factor anymore.
But today it's about 8 bits of data. So here's a pretty graph that explains exactly what's happening. So imagine that the x-axis is the pixel position. So 0 is the first pixel at the bottom of the screen, 1 is the next row of pixels, and so on. If we had the perfect gradient going from white to black, or black to white, that would be the green line. So we have, that would be an analog signal. We have the perfect value for every pixel on the screen. Now, when quantization happens, because we only have 256 shades of color, we get the red curve instead. And what you can see is that every possible color in our gradient occupies multiple positions on screen. And this is where the bending is coming from. And it's something that, if you ever see bending, and I have that discussion with UX many, many times, and I try to make them understand that if you only have 250 colors, you cannot render them properly on more than 256 pixels because there's just not enough data. So there's a solution to that problem that's called dithering. You might have heard of it. We have a couple of APIs on Android that let you enable dithering or turn off dithering. But before we talk about it, I just want to talk about where dithering comes from, because I found the story while I was preparing the slides, and I think it's pretty interesting. So it came from World War II. Planes and boats used to have mechanical computers that were used to compute the trajectory of bombs, missiles, that kind of stuff, fun stuff. And engineers were working on those computers. They realized that when the computers were on the ground being worked on, repaired or tweaked or whatever, they were not as accurate as they were when they were in the air or at sea. And they realized that it was because of the vibrations of the boats or the planes themselves. So what was happening is that because those were mechanical computers, they were full of gears, and gears have those teeth, and they have a limited number of positions. So gears would tend to get rusty or get stuck because of the grease or whatever. And the vibrations of the engines of the plane or the boat were just jittering the gears enough to get them unstuck. So the solution they came up with was to add vibrators to their computers. So they added motors inside the computers to just vibrate them to increase precision. And this is exactly what we need to do to fix bending. You can imagine that we have those red bands. Now, if we were to disrupt that signal and just jitter it at every position, we would, on average, have something that's closer to the green line. And the word dithering, I think, came from the German translation of jitter or something like that. So let me show you a demo to show you what dithering looks like. So this is a little shader I wrote where at the top I have a gradient, I have multiple gradients, and I'm quantizing them way more than they actually would look like on your screen, but it shows the effect. And here vertically, every row is a different way of dithering the pattern and to make it smoother. So to be clear, the gradient you see at the top is the same gradient you see in every row. It's just I've added some noise to every row to make the gradient look better. And what's really impressive with dithering, it works pretty well already, especially if you squint. So it turns out that in graphics, for a lot of things that we do, we have something called the squint test. We just squint at the screen, and if it looks good when we squint, that means we're on the right track. So if you squint, the gradients will look great. And I can go to even 2 colors. So if I quantize all the way to 2 colors, and you squint a little bit, you'll see that the gradients look like gradients, even though we start from only 2 solid colors, which shows you how powerful dithering can be. And if you were playing games a long time ago, if you had an Apple II or a Commodore 64 or one of those, you have probably seen this pattern or something very similar. And we'll talk about this pattern.
And if you had
again.
a Mac in the 80s, you saw the gray pattern.
Yeah, that one. Present. How do I go back to present? God, I hate slides. There you go. All right, so this is what, before Android O, this is what we used to do for dithering. We used something called ordered dithering, so that's the Apple II version. It uses a 4x4 Bayer matrix. So Bayer matrices are used in a number of situations. For instance, they're used in camera sensors. That's how we get RGB colors out of those sensors. And you can see, so that's what the pattern looks like. And this is an example of a gradient once we apply the pattern. So if we zoom in on it, it looks pretty disgusting. And you can even see the pattern. So we said that this pattern is isotropic because we can see the strong vertical and horizontal line. We can see the shapes. It's a tiled pattern, and we can see the repetition. So it works pretty well, but it doesn't always work. There are some gradients where it looks horrible. The technical term is that it looks like shit. So in O...
That's a translation from the original German word.
Actually, it's probably likely. So here's what I did in O instead. Instead of using this fixed pattern that was basically a texture that would overlay on top of the gradients, we generate on the GPU a uniform noise. It's randomized. It depends on the position of the pixels. And we do some fancy triangle reshaping to make it look better. It's still monochromatic. That means every color channel, R, G, and B, we apply the same noise value. We could do better, but it is anisotropic. So if you look at the picture here, it looks more noisy than before, but you don't see those regular patterns anymore. So once it's on the high resolution, high density display, the feel is much more natural, and it looks a lot better. It also works on more gradients. For instance, the previous pattern works great when your gradient is horizontal or vertical, because it follows the shape, basically, of the pattern. But on radial gradients, on circles, it didn't work at all. This works in many more situations. We're also now applying the dithering to the alpha channel, which helps a lot if you're going to blend several layers on top of each other. So we could do a lot better. I've been experimenting with other techniques, so we could do temporal dithering, where on every frame we change the seed of the random number generator. You effectively get a form of 3D dithering. It looks fantastic. The problem on Android is that we don't render all the time, so we can't really like do that. I should try. Maybe it will look fine. I don't know. I'll try. Chet will probably yell at me. We could do chromatic dithering, where we apply a different noise to every channel to further, blur things. We could use something called blue noise that looks very organic. It's by far the best noise we could use for dithering. It's a little annoying because a 64 by 64 blue noise texture takes about 2 hours to generate on a MacBook Pro.
That is serious jank.
Yeah, so we can't really do that at runtime. We would have to pre-generate the texture, and we would recreate a pattern. Blue noise is pretty good at being tiled, but I don't know if we're going to do that. And we could also dither in many more places. So in O, if you looked at the release notes, we're doing color management, so we're going to start using 10-bit and 16-bit bitmaps or windows. So that means that at the end, when we go to the 8-bit display, we could use dithering there to preserve the colors that we had, the high bit depth that we had.
You can also do your own spatial dithering. When you look at your phone, just shake it a little bit. You get sort of a natural smoothing function.
You jest, but it turns out that there are two things that are also helping us a lot on modern devices. Pen-tiled displays, which I absolutely hate, but by their very nature of not having all the RGB component per pixel, they are a form of dithering that helps on the high-density displays because our eyes also help by blurring everything, like the finer details get blurred together. So dithering got even better with hardware, like I would say wetware acceleration, thanks to our eyes. So what you can do in your applications. So 565 bitmaps are tempting because they use half the memory of regular RGBA 888 bitmaps. Now, it's fine if you generate a 565 bitmap from Bitmap Factory. So you call Bitmap Factory, you want to decode a JPEG or a PNG, and you say, please give me a 565 bitmap. What we're going to do is we're going to load the bitmap in 8888, apply a dithering pattern, and you're going to get something that looks pretty good. You've seen that with the gradients. We can do like a very good job at dithering, and especially on those high-density displays, it's going to be fine. Do not render into 565 bitmaps unless you really, really have to. But if you do, what's going to happen is that everything you render into the bitmap will increase the error because we're going to quantize even more every time you render into it. And if you turn on dithering using paint.setDither, you're going to overlay dithering on top of dithering on top of dithering, and you're going to multiply the error, and it's going to look horrible. If you go back to Android 1 with an emulator, you're going to see those nasty effects all over the place. And with 565, because we have more precision in the green channel, we tend to get green bands that look absolutely disgusting. Also, if you use gradients, and you use alpha gradients, so you use the alpha channel, it's not just two solid colors that you have in your gradient, you are making bending worse, because what's going to happen is that we're going to do the quantization first to generate that gradient, then we're going to blend on screen. What we want to do is first do the blending at high precision, then do the quantization. So I have an example here. I don't know if it's very visible on screen, but on the left, I manipulated the image in Photoshop, so it doesn't look nearly as bad on an actual phone, but yeah, you can't see anything. You can, sorry. You can probably kind of guess, can you see the bands? You should be able to see like circular patterns here. Everybody's dead. Anyway, so you can see a lot of bands here, and that's an alpha gradient from a bright color to whatever to completely transparent on top of this dark background. Now, if instead of using an alpha gradient, we bake the background color into the gradient itself, we still get bending, but a lot less bending. You can see like here the comparison. We still see the bands here, and they're a lot less visible in this case. It also has the added benefit that, and there's no way you can see that. You can see it. So the dithering pattern will be everywhere, whereas with the alpha gradient, the dithering pattern will not show up on the background. So you see a cutoff. The dithering pattern stops where the gradient stops, and it looks a little bit weird. So if you render a gradient on top of a solid color background, just don't bother with a solid color background. Like, first of all, you're going to reduce overdraw, which is going to be more efficient, but you're also going to increase quality. And whatever you do, like, try to avoid doing an alpha gradient on top of an alpha gradient on top of an alpha gradient, because you're just going to make things worse and worse. And do we still have more time?
About 2 minutes.
All right, we can do trilinear filtering really quickly. It's been around for several years on Android. I just wanted to talk about it again in case you're not aware of it. So let's say we have a source image. We want to render it at half of its size. We can do that really well on Android, and this is what happens. So to render 1 pixel in the final image, we take 4 pixels in the source destination, so 2 by 2 square. We do the average, and it's great because we divided the size in half, and that's exactly how we do the blending. But what if we want to draw that image at less than half of its size? What happens is that we're still going to use the same 2 by 2 pattern, so we're going to start dropping information, and we're going to lower the quality. So to combat that, there's a technique called trilinear filtering. It's also called MIP mapping. And this is how it works. So you start with an image. Then you divide the size of that image by 2. Then you take that image, you divide its size by 2, you take that image, and so on, until you reach a 1-by-1 image. And you keep all those images. Then what we do is, when we want to render 1 pixel in the destination of the final image, we take the 2 images of that what's called a pyramid. We take the 2 images that are the closest to the final size you want. In each one of those images, we take 4 pixels, we do the average, and then we average the 2 results. And that preserves all the information from the original image. So I have an example here. If you look at this image, if you look here on the diagonal, or over here, I hate you slides, you can see a lot of aliasing artifacts. That's because we've dropped information. We went from a very large image to a...
Can you zoom in?
Yeah, I can zoom in. Yeah, you can see the aliasing here and here. With trilinear filtering, because we can preserve all the information, we can keep smooth edges. So it's very powerful, especially if you're getting large photos from a server or something like that. It's also pretty cheap because each level of that pyramid is a quarter of the size in memory as the previous level. So the total cost is 30% of the original image in terms of memory. So it's not that much. And just another story time. So I said that this is a technique called MIP mapping. And the MIP part of the word I discovered comes from the Latin multum in parvo, which means much in little, because for 30% more memory, you can get much better results.
MIP mapping was actually invented in Rome.
It was not.
In the year 50 BC.
It's also very easy to use. If you want to use it, you call set has bitmap true on a bitmap, and you're done. If you go through the hardware accelerated code path, you're going to get the higher quality. Also, the extra memory usage is going to be in video RAM, so it's not going to count against your Java heap. So you're not going to get an out-of-memory exception because of it. And if you have a drawable, you can also set the MIP map attribute to true in XML. And that's it. We don't even have a Q&A slide.
We don't, which is fortunate because we are way out of time. Thank you for coming. We hope you learned something.